Okay, so this is a video on significant testing. Significance testing for means. Okay, so kind of the upshot of things here is you're going to get a null hypothesis that the mean is some value for the population. You're going to get an alternate hypothesis that the mean is either less than, greater than, or equal to some value. Sorry, that shouldn't be 0. That should be some value. So let's make that value a number, right? A number. And what we're going to have here is we're going to have some sample data. We're going to have the sample mean, we're going to have a sample standard deviation, and a sample size. And what we've learned so far is that if you work this against a t distribution, you can get a t distribution. So this thing is going to be, so the sample means, right, are distributed by t with the center at the mean, with the standard deviation of x over the square root of n, given t with n minus 1, so this would be n is my sample size, n minus 1 degrees of freedom, right? And what I want to do is I want to look at that t distribution, which looks a lot like a normal, but it's either flatter, it's probably flatter, right? It's going to be centered here. And what we're going to do is, excuse me, assuming the mean is, the null hypothesis is true, we're going to create a t-test statistic, right, which is going to be my x bar minus my mean over the square root of, over sx over the square root of n, right? So this gets me my t sample statistic, and let's say this is here, and here's my t sample statistic. And then, given the true null hypothesis, what is the probability? This is my p-value. The probability that I get that sample statistic or one more extreme in the direction of the alternate hypothesis. So this would be the p-value for the greater. If I made the arrow over here, then it would be p-value for the less than. And if I could put the arrow on both sides, it would be the p-value for the not equal to. Right, so that's what we're dealing with there. So let's actually walk one of these through. And just like the confidence interval, you can either do this from, what do you call it? The parameters, right? Your statistics, sorry, not parameters, your statistics, the x bar, the sx, and the n, or you can start with the data itself. So let's look at a problem. All right, so let's look at a little bit of a problem here, because I think this is one of the ways that we could approach this. We have a sample set of data here. So we have, all right, so the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 different locations along a stream. Here are the results in milligrams per liter. An average dissolved oxygen level below 5 puts aquatic life at risk. So the data provide convincing evidence at the alpha equals 0.05 significance level that the aquatic life in the stream is at risk. Okay, so kind of working from this a little bit, my H null here is going to be mean equals 5 milligrams, right? My alternate hypothesis, which is my claim here, is going to be that the mean is less than, right, 5 milligrams per liter, milligrams per liter, right? Because if we're below that, we're putting aquatic life at risk, and I'm testing with an alpha of 0.05. So I'm going to let the calculator do the heavy lifting here. So me a moment, and I'm going to get all this information into the calculator. Okay, so I went ahead and did a little bit of off-screen work here and just entered the 15 data points from our problem into L1 in the calculator. Okay, so what I want to reach for here is I'm going to go stat tests, and I'm going to t-test because I'm working with a t-distribution. And I'm going to get my data, right? So I'm testing against a null hypothesis at 5. My data is in list 1. I have a frequency of 1, and I'm testing against the alternate hypothesis, which is the less than. So I'm going to go ahead and calculate that. And you can see there's my t-test statistic, which is like negative 0.951. My p-value, which is the significant one here, is 0.178, right? Which is a somewhat large p-value, right? My mean for my data is 4.769. The data standard deviation is that. 15 is the n, so I'm working with 14 degrees of freedom. But this is the key number here, this 0.1786, so we'll make that 0.179, right? So we get a p-value of 0.179. Now remember, p-value large means fail to reject the null hypothesis. So we're going to say it is possible that the mean of the mean level of dissolved oxygen in the stream is actually 5, right? Or the mean level in the stream is actually 5. Okay, so even though we've got some pretty low samples in here, it's possible that mean value is actually 5 for the stream itself. Now, so this means that we do not have convincing evidence at the 0.05 significance level, because p is bigger than 0.05, that the aquatic life in the stream is at risk. So there you have it, a pretty simple test. You can also do this test using, right tail or two tail, or also can do this test with what do you call it? Sorry, not the data, but rather just the statistics. Right, so if you just had the sample mean, the sample standard deviation, and the sample size, you'd have enough to go on to actually draw the correct inference. Okay, so there you go. There's an example of this. There's a little bit of discussion again of power in the notes. Keep in mind we did discuss this as we did the end of last unit. Power is given a particular null hypothesis being true. What is the probability of getting a sample that supports the alternate hypothesis? So that's just a term to have in the back of your head, that given that a particular null hypothesis is true, what is the probability of getting a sample that supports the alternate hypothesis, right? Okay, so we're going to stop there, and now we'll see you in class.